Good afternoon, everyone. I hope you can see and hear me. My name is Steve Fitzpatrick, and I'll be doing a webinar about high-resolution particle size analysis by differential sedimentation. We have our host, Wendy, is monitoring the presentation, and if you have questions you want to ask at the end, please send them to Wendy by chat. You have a chat bar there, and she will record them. And at the end, I will try to answer as many as we can fit in. Please note that this presentation as a PowerPoint will be available to you as well, and the webinar is being recorded, and an MP file of the actual presentation will also be made available. So we can get started. This is the overall content of the webinar. I'll talk a little bit about the history of the technology, where it came from. Then we'll talk about theory of operation, how the process goes, and the different steps that are involved in calculating the final size distribution. And then finally, we'll have a few example practice requirements for broad distribution, low density samples, and some specific interesting applications. Okay, the history, I started working on particle size characterization in the mid-1970s. And at that time, there were really very few ways to measure fine particles. So if the particles were below the wavelength of light, below about 500 nanometers, you simply couldn't easily characterize them. We did have limited access to an electron microscope, but it was slow and expensive. So we were kind of stuck, and the research we were doing required that we control and adjust the particle size distribution in the range from about 75 nanometers to 5,000. With that requirement, we began to think about how we could do this with sedimentation by Stokes' law. And we naively built a hollow disk, filled it with water, and expected we could inject the sample and get wonderful results. And of course, it didn't work at all. It took a couple of months of effort to begin to understand why it didn't work. And the breakthrough that came there was the requirement for a density gradient to get a stable sedimentation. And we'll talk about that in some detail. Many years later, we began commercial production in 1994. And there are currently some 640 plus instruments around the world. There are dozens of applications. When people ask, well, what do you use your instruments for? I say, well, there's so many applications I can hardly list them. There are dozens, and they range from as small as 4 nanometers for gold sols to 20 microns or more for some coarse materials. So we'll start with the theory. Particles sediment in a fluid according to Stokes' law. Sir G.G. Stokes developed the measurement technique in the 18th century. The velocity of sedimentation is determined by a balance between two forces, gravitational force downward and viscous drag upward. When those two are in balance, the motion of the particle is constant in velocity. And the factors that control that velocity are the gravitational field strength G, difference in density between the fluid and the particles, the fluid viscosity, the particle diameter, and the particle shape. Stokes worked with spherical particles or nearly spherical particles. The velocity is given by the equation here below. If I get a pointer on it, velocity is equal to difference in density between the particles in the fluid times G times diameter squared, all divided by 18 times the viscosity. When you rearrange that equation, you can solve for diameter based on velocity. So if you measure the velocity and you know the parameters that make up the rest of the equation, you can determine the particle size diameter directly. Now, for the measurement to be accurate, the particles have to be low in concentration, and by low in concentration, we mean not more than a couple % solid content. Particles have to be far from the walls, and by far from the walls, we mean more than 1 or 2 diameters away from the wall. If a particle is a 1 micron particle, it needs to be more than 1 or 2 microns away from the wall for there to be no effective drag on the wall. The particle has to sediment at a speed where the fluid flow around the particle is smooth and laminar and not turbulent. Fortunately, most of these requirements are easily met in the Disc Centrifuge. Now, there are 2 kinds, excuse me, there are 2 kinds of sedimentation that you can use to determine particle size distribution. Homogeneous sedimentation begins with a homogeneous mixture of all different sizes, which are then allowed to settle. The largest particles sediment out, and the loss of the particles can be monitored by a detector beam. At the end of the measurement, all the particles have settled out and you have just clear fluid. Differential sedimentation starts with 100% clear fluid, and you inject a sample of particles, all different sizes, on top of the clear fluid. The largest particles sediment quickly, the smaller particles sediment more slowly, and at the end of the measurement, the entire liquid becomes clear. So the two methods both measure particle size distribution, but the way you handle the data has to be different. This is a comparison of a differential distribution and a homogeneous or integral distribution. And it's important to understand that these 2 curves, as you see here, excuse me, these 2 curves represent the same exact data. And you can convert the integral distribution here into the differential distribution just by doing first derivative with respect to particle diameter. And the converse, if you do an integration over diameter for the differential distribution, then you will generate the integral distribution. So the 2 are equivalent in terms of content of information. The big advantage of doing a differential distribution rather than a homogeneous one is that you can run many samples in a row with a homogeneous, with a differential distribution, whereas for a homogeneous distribution, you have to put a complete sample in, mix it all up uniformly for each sample. That means that your instrument has to stop and start for each sample, whereas with differential, you are able to run many samples continuously. The other advantage is that the mathematical process of differentiation tends to add high frequency noise, whereas the mathematical process of integration tends to suppress high frequency noise. So by collecting the data as a differential distribution, you end up with a consistently better signal to noise ratio across the entire size range. This is a simple diagram of the disc centrifuge, a cross section. As you can see, there's an axis of rotation, and inside of the rotating disc, there is a ring, essentially a ring of gradient fluid, density gradient fluid. And to run a measurement, you inject a sample along the axis of rotation with a syringe, small volume, 100 microliters approximately, and the liquid then sprays onto the surface of the gradient very rapidly because of the rotation of the disc. And once on the surface, the particles themselves begin to sediment outward until they interrupt, that is, come in contact with the detector beam. The particles scatter some of the beam or absorb some of the beam, and so generate an attenuation signal. Now, inside of a centrifuge, Stokes' law has to be modified because the g-force is not constant. The g-force in a centrifuge is proportional to both the distance from the center of rotation and also proportional to the square of the rotational speed. So we have to convert the original Stokes equation into one that is suitable for a centrifuge, and that is shown here. You'll note the same value, 18n, but now we have a logarithmic function. R0 is the radius of rotation, the distance from the center of rotation at the fluid surface, and R is the radius at the detector. Rho fluid and rho particle the same. Omega is the rotational speed in radians per second, and time, of course, is in seconds. You can combine all of these parameters except time into a constant value, and you see here that it simplifies a great deal. It basically, the diameter is a constant times the time elapsed to the 1/2 power. What that means, of course, is if you double the time, if you increase the time by fourfold, it's a twofold reduction in diameter. Now, one other thing to keep in mind about Stokes calculation is it's a first principles calculation. That is, it's not dependent on any approximations. It's based on measured values, and you can determine the absolute size accurately if you know all of the values for all of the parameters in the equation. In practice, and what we do with the Disc Centrifuge is we use a calibration standard, because to determine each of the many parameters exactly is a challenge, whereas with a calibration standard, nearly all of those parameters are eliminated and you don't need to measure them. You will rely on the calibration standard to get the accuracy. Now, some people have particles that are non-spherical. The most common shape for a particle is, of course, spherical or nearly so, but there are many particles that are not spherical in shape, and so the question always arises, how much does the change in shape change the apparent size? And just so that we're on the same page here about what we're talking about, imagine you have a non-spherical particle, say, for example, you have a cube. If that cube were converted into a sphere of the same volume, and you measured that cube versus the sphere, the question is, how much would the apparent size of the cube be compared to the sphere of the same volume? And on the right here, you can see a column of numbers. These are how much smaller the non-spherical particle is compared to a sphere of the same size, same volume. And you can see that the particle has to become remarkably non-spherical before the error in measured size becomes very large. There are some particles, for example, nano rods or carbon fibers, things like that, that can be so non-spherical that they give numbers that are very far off. But for the most common kinds of shapes, the numbers are not far off at all. And it's possible, if you know the shape of the particle, you can substitute an adjusted density value for the particle, and that will compensate for the known increase in drag. Now, when you do differential sedimentation, the key requirement is that there must be a density gradient present. If there's no density gradient, then you can't make a measurement at all. And when I was developing the technique many years ago, I didn't have a density gradient, and so I got no results. The requirement for stability can be given mathematically as the first derivative of the net density of the fluid with respect to radius of rotation, that is distance from the center of rotation. That net density must be constantly increasing or not decreasing. So if you go from the surface of the density gradient to the outside edge of the density gradient, there's a continuous increase. And that continuous increase ensures stability of sedimentation. And by that, I mean the particles actually sediment as particles and not as bulk material. If you don't have a density gradient, you get what is called instability or streaming, and this series of diagrams shows how that process takes place. There's actually a couple of names for it: Rayleigh-Taylor instability and Kelvin-Helmholtz instability. But you can see what happens here. If you try to put a more dense fluid on top of a less dense fluid, inevitably the more dense fluid will begin to penetrate the less dense fluid and displace it. And as it penetrates and displaces, it becomes ever more violently mixed in. And finally, you get what look like long streams of particles in the lower density medium. And this is exactly what people saw for many years when they tried to do differential sedimentation. It just didn't work very well. And many instruments were sold in the past that had strobe lights and that sort of thing, so that you could actually with your eyes see if the sedimentation was stable. By using an explicit density gradient, we don't need to worry about whether or not the sedimentation is stable because we are certain that it is. So what are the characteristics of density gradients? They're made from at least two components, one higher in density than the other. They're formed either manually or by stepwise additions or with a density gradient building machine. The components have to be miscible with each other, but also they have to be compatible with the particles. And finally, a three-component density gradient, if you choose the components correctly, can have a variability in density, but constant refractive index, which is advantageous sometimes. Okay, the lifetime of a gradient is set by the molecular diffusion of the components in the gradient. The higher the molecular weight, the more slowly the molecules diffuse. If you wait long enough, the gradient eventually collapses because diffusion makes the concentration uniform across the whole of the liquid. But you can make the gradient last longer by increasing molecular weight, and I've given an example here. Dextran, which is a polyglucose of 10,000 Daltons compared to sucrose of 342 Daltons, and these two solutions at the same concentration will have identical refractive index, identical density, but that the Dextran will have approximately 10 times longer useful gradient lifetime. In other words, you can run the instrument continuously for a couple of days without having to replace the density gradient. One other thing for existing users to keep in mind is that when you inject calibration standards and samples, the fluid that you inject stays at the surface. And so that fluid that you inject tends to diffuse into the gradient and rejuvenates it. That is, it increases the steepness of the gradient by dilution from above. And finally, at a sufficiently high molecular weight, it's possible to make infinitely stable gradients. And here's an example of one. This is a gradient that's formed from a dextran with a molecular weight of 40,000 Daltons and spinning in a disk at 22,000 RPM. This is a calculated result, but we've used it and we know that it's pretty close. This is thermodynamically stable. It doesn't degrade over time at all because the G-force in the centrifuge is just enough to balance the diffusion upward of the more concentrated dextran, and the two processes completely balance, and the gradient is indefinitely stable. This particular gradient I've tested for periods of 400 hours with no degradation at all. The only problem is that you have to be careful to not lose water over many days by evaporation. Now, I want to talk a little bit about resolution. Resolution is something particle characterization people talk about all the time. Sometimes they tell fibs about it. Sometimes they're more honest about it. But in any case, there are a couple of different ways to characterize resolution. One is the overlap of two narrow peaks. How much full separation do you get? On the left, I've shown a diagram. The red line here in the center represents what you would see in your data, and the blue lines show the underlying overlap between the two samples. And In that case, I'm saying 2.5% of the area of each sample overlaps with the other, so 95% separation. On the right is a single peak, and it has a width at 95% inclusive of 100 nanometers versus a mode of 550 nanometers. If you calculate the resolution, it's the same for both. My preference is for this method here because it's simpler. It doesn't require multiple materials. And I call the resolution the minimum reportable peak width for either 95 or 99% inclusive. In other words, if you had a perfectly narrow sample and you measured it with your instrument, whatever the instrument is, without arm waves and without mathematical manipulation after the fact, what is the width of that perfectly narrow sample? And that's the resolution of the method. So what are the resolutions for typical sizing methods? I've listed a few here. There are lots of different methods, of course, but these are some common ones. The electrozone counter, a long time ago called a Coulter counter, developed by Walter Coulter in the 1950s. The electrozone counter has a resolution of 10 to 15%. A perfectly narrow peak will be reported as 10 to 15% as wide as its mode diameter. Laser diffraction, depending on the instrument, has 15 to 25% resolution. Photon correlation, or DLS, has approximately 50% resolution. Sedimentation field flow fractionation is quite good. It's 5%. Cross-flow field flow fractionation related to sedimentation field flow is 10%, and of course the Disc Centrifuge differential sedimentation better than 2%. I want to emphasize that these are based on our experience in actually using these instruments. It's not a guarantee of accuracy. Maybe someone has developed a new laser diffraction instrument that's better than this, but everything that we've seen until now is consistent with the numbers I've shown. So if you look at these, you can see the advantage of differential sedimentation and why it's so high in resolution as a particle characterization method. Now there is a calculation that I call the basic resolution, and the basic resolution is what the instrument can report with no Brownian diffusion. And this simple equation here gives you an idea where RD is the radius of the detector. Oh, my goodness. RD is the radius of the detector, and RS is the radius of the fluid surface. And if you look at this equation, you'll see something interesting. You can increase, if you want, the distance that the particles sediment, RD to RS, make the disk bigger, make the sedimentation take longer. And if you do that, you can get to extremely good resolution. In fact, you can get to resolutions essentially without limit if you're willing to wait long enough for the results. And here's an example of how the fluid volume in the centrifuge changes the minimum reportable peak width. As you increase the fluid volume, you see the curves out here on the larger fluid volumes, the minimum reportable peak width becomes smaller and smaller. But this purple line here shows the relative measurement time. So if you have a very big gradient with a long sedimentation path, you'll have excellent resolution, near 1%, but at the same time, you'll have a measurement that takes 3 times longer, or nearly 3 times longer. So it's a trade-off between resolution and measurement time. Now, the ultimate resolution that you can reach with the Disc Centrifuge depends on Brownian motion. All particles smaller than about 4 microns have Brownian motion, and it causes diffusion. Because of the G-force in the centrifuge, Brownian diffusion is usually insignificant compared to sedimentation velocity for nearly all particles larger than 200 nanometers. In other words, if you're measuring 500 nanometer or 1 micron or 2 micron particles, Brownian diffusion simply doesn't contribute anything to the reported distribution. For very small particles, especially below 100 nanometers, Brownian diffusion causes broadening of the peak. And at a very small size, diffusion becomes comparable in speed to sedimentation, and the resulting distribution will always be relatively low compared to the basic resolution for the method. And this simple diagram shows how Brownian diffusion progresses over time. You can see the series. It's Gaussian curves that form as the particles diffuse. And we can think of that Gaussian curve as an uncertainty function that's superimposed on the deterministic measurement. In other words, the particles are sedimenting continuously under g-force at a deterministic rate, but they're also undergoing diffusion at an uncertain rate, and particles go in different directions randomly. So we have a broadening of the reported peak that represents the uncertainty in the position of individual particles. Here's an example from real world. This is SiO2 particles of different sizes. You can see that as the size goes down, the best resolution you can get keeps getting worse. And below approximately 13 nanometers, the resolution becomes quite poor, and it would be pointless to measure any smaller than that. The same applies to every kind of material. And here's a curve that represents how that Brownian diffusion influences the minimum practical size. So for a low density material like polystyrene here, you see the minimum size that you can practically measure before Brownian diffusion becomes too great is in the range of 40 nanometers, whereas SiO2, it's more like 13 nanometers, and gold sol with a density of 19 can be measured to as small as 4 nanometers before Brownian diffusion overwhelms. Okay, once we've measured the size of the particles, we need to quantify how much is there, and the way we do that is by using a light beam. The beam, as the particle passes through, the beam is scattered partially, and we see a reduction in beam intensity and absorption fraction, and that is used to calculate the quantity. Now, this is all done based on scattering theory. And scattering looks like this. You know, the incident beam comes in from the right here, hits the particle, light is scattered in all different directions, but a portion of the light is scattered at a narrow forward angle. If the narrow forward angle still goes into the light sensor, then that is not being reduced, it's still being sensed. So in order to do an accurate calculation of quantity, we need to calculate not just the total scattering, but also the fraction that is forward scattered. The larger the particles become, the more the forward scattered light is important, and a significant fraction of scattered light still reaches the detector when the particles are very large. There is a parameter called Qnet, and that is the ratio of the particles' attenuation cross-section compared to its physical cross-section. Physical cross-section is just, you know, a circle, but the attenuation cross-section can be larger or smaller than the circle that represents the particle. And this diagram shows how Qnet, the ratio of the scattering to physical cross-sections, how it changes with time. This is for polystyrene particles, and you can see remarkably that particles near 1 micron in polystyrene right here, they scatter almost 2.5 times as much light as you would expect them to based on their physical cross-section. As the particles get larger and larger, they scatter less light, and they also scatter at forward angles. So we see a Qnet that drops continuously as we go up in size. Finally, note that there's a oscillation going on here, and this oscillation has to do with how the light multiple integral numbers of light waves across the particle. And you see this as a characteristic in all scattering by spheres. If the particle has optical absorbance, that is, if it can also absorb and turn some of the light into heat, it completely changes the way that the Q-net functions. You see the dark blue line in this graphic is very different from the original polystyrene scattering curve. And of course, the calculation is done using a complex refractive index. That is, the refractive index has the real part, which is n, and it has an imaginary part, which is how we handle the absorbance of light. The complex refractive index is used in all me calculations, and you should keep in mind a couple of things. It's not so easy sometimes to find the imaginary part of the refractive index, but if you hunt, you usually can find it. And the other thing is to keep in mind that the published values for refractive index are almost always at the sodium line. That's 589 nanometer wavelength. And the real refractive index at a shorter wavelength, like we use in the Disc Centrifuge, is going to always be higher. So here's a quick summary about light scattering. Attenuation of the beam is converted by the software into a weight of particles. The measured quantity is quantitative. We actually measure how much weight of material is there. And when the optical constants are correct, the reported total sample weight will be close to the actual weight that was injected. And we have users who routinely use the instrument for quantitative work. Accurate values for both the refractive index of the particles and the gradient they pass through have to be used to get accurate distributions. And we always have to use the K value, of absorption constant, when particles absorb, or once again, we'll get very inaccurate results. Okay, we'll talk a little bit about some practice. Sometimes the distribution is extremely broad, and that presents a problem because at a single speed, the dynamic size range can't be too wide, and the dynamic size range is defined as the largest particles in the sample to the smallest particles in the sample. In order for the instrument to get accurate data, the largest particles should arrive at the detector no faster than 1 second after injection. If the smallest particles are 2% as large as the largest particle, that represents a dynamic range of 50. The analysis time will be about 42 minutes. If you try to do a measurement at fixed speed over a very wide dynamic range, say 75 or more, the analysis time becomes impractically long. So how do we solve the problem of very broad distributions? We use a special insert that separates the disc into two chambers so that the speed can be changed during the measurement without disrupting the gradient. And when we do that, we can expand the dynamic range because we start the disc at a slow speed, measure the large particles, and then slowly increase the speed to measure the smallest particles. An example of the impact of speed ramping is at the bottom here. It makes a tremendous change in the measurement time to use speed ramping. This is what they look like. They're plastic polyethylene pieces that fit snugly and seal against the disc surfaces so that when the speed changes, the fluid inside the disc can't rotate relative to the disc. It has to stay at the same speed as the disc. There's a cycle you start at a minimum speed, collect data for 60 seconds at that minimum speed, and then gradually increase the speed at approximately 40 RPM per second. And when you reach the maximum speed, you hold until the end of the measurement, and finally slow back to start again. So there's a ramp cycle that's repeated for each calibration and each measurement of samples. Okay, the disadvantages of speed ramping are that you have to spend the time to slow the disc back down to the starting speed, and that costs you time. Increasing speed also increases internal air friction and heating. So if the maximum speed is over 12,000 RPM, that means that during the run, the temperature inside the instrument is changing. And because the temperature is changing, there is some uncertainty in the density gradient viscosity. Fluids generally become less viscous as the temperature increases. So there's an uncertainty in the measurement results, not large, percent or two, but it is there. In general, it's unwise and unnecessary to use speed ramping if the true dynamic size range is much less than 75. Now, for low density samples, it's another challenge. Particles that float in the liquid they are suspended in can never sediment to the outside of the disc. They want to float on the surface. We use a special disc that I developed back in the early 1990s. This disc allows the sample to be deposited at the outside edge of the fluid instead of on the surface, and then the particles float towards the surface. The calculations, according to Stokes' law, are identical. It's only a sign change. A special injection port is used to guide the syringe needle that holds the sample into the correct position for injection. This is what the low density disc design looks like. You can see here that there's a central closure like normal here, but instead of injecting into the center, you actually inject into a groove that's machined into the face of the disc. And the groove has 4 capillary channels. You can see them here in black. Those capillary channels connect the base of the groove with the bottom of the disc chamber. So when you make an injection, the sample you inject runs down the capillary tubes, spreads on the bottom, and then the particles float towards the surface. The sample that you inject has to be suspended in a liquid that is higher in density than the most dense liquid that forms the gradient. And that's so that the injected material will spread evenly over the bottom and allow the particles to start uniformly floating towards the surface. When we use low density measurements, we have to move the detector beam. Its normal position is about 2 or 3 millimeters from the outside edge of the disc. We move it to approximately 10 millimeters from the outside edge of the disc so that the particles have a long sedimentation path during the measurement. There are a couple of disadvantages for low density measurements. When you inject the sample, we look back here, when you inject the sample runs to the bottom and spreads over the bottom, and that means that the entire gradient is lifted slightly upward. That is, it is raised by the injected sample. So when that liquid rises, it has a radial speed which is the same, but now it's on a smaller radius of rotation. And what that means is you basically are accelerating the rotational speed of the gradient slightly compared to the disc. It's a very small increase in speed, but it's enough to cause a small baseline artifact when the sample is injected. It's possible to subtract that artifact, but it is almost always present. You also have to change the type of injection port between when you form the gradient, which is formed through the center opening, and when you inject samples. And you have to take great care to avoid cross-contamination because the capillaries hold about 9 microliters or 10 microliters, and when you inject samples in a series, a little bit of the preceding sample remains in the capillaries. So you generally have to clear the cross-contamination with injection of clear fluid between the samples, which adds to your measurement time. Yeah, I show here what the issue is. The cross-contamination takes place from the fluid that remains in the capillaries. Okay, here's an interesting example. This is a stirred tank continuous reaction. This was a company that was precipitating SiO2 out of solution, continuously adding all the raw materials to a stirred tank, and they expected a broad single peak distribution, and they got, in fact, 13 peaks, I think. And what was happening is that, like many stirred tank reactions, this was an oscillating process where particles were forming only when the total surface area available in the reacting mass became too low to accept what was being formed, and then new particles would form. Each time a new family of particles formed, a new peak was formed. And you can see that the peak starts small, it grows, and then finally diminishes as it washes out of the reactor. I found this very interesting because I had seen the same thing in many kinds of continuous reactors. Okay, one of the questions that people often have with particle characterization is, when they have a broad distribution, how can they verify that the broad distribution is actually accurate? In other words, you can inject a narrow peak and you know that it's reported to the right size, but how about a broad peak? How can you be confident that broad peak is accurate? And one technique to do that is to take narrow peaks and superimpose them on a broad peak. And if you know the quantity and the size of each of those narrow peaks, and they are reported correctly, as I've shown here for the blue trace, then you can be certain that the red trace, the one without the small particles added, is accurate in both size and quantity. Okay, here's another useful and interesting application. Often people have to disperse dry materials, often with sonication or intense mixing. And the question always is, have I fully dispersed the sample or not? And so the sample, in this case, starts as a dry powder, sonicated over varying periods of time, starting at 30 seconds and ending at 720 seconds. After each sonication, the same sample is measured, and you can see what happens. You see at first rapid improvement in particle size, reduction in size, and then at the end it's hardly moving at all. So you can be reasonably sure that at the end, at 720 seconds, the dispersion is complete. Okay, it is time for questions, if any have been raised.
Yes, thank you, Steve. Well, there are a few questions. First is a question from Arie van der Marel. Arie van der Marel is, of course, Dutch, and he's asking the following. He says, we are not able to measure polystyrene smaller than 80 nanometers. Probably we need another gradient instead of sucrose.
Yeah, it would help a great deal in a case like that when the analysis is extremely long and polystyrene below 80 nanometers becomes long. It's better to use a higher molecular weight material like Dextrana 5000 or 10,000 because then the gradient is more stable, the baseline is more stable, and the gradient will not collapse during the measurement.
Okay, well, thank you. I hope that's good enough for you, Mr. van der Marel. If you have any questions, you can send them to me and I will make sure they will get answered. Next question is from Nick G from the UK. For a peak that's moderately broad, he says, how do you determine whether the peak width arises because of a diffusion process or because there's a range of particle sizes? I think that's a few slides before this when you were talking about the peak.
Yes. Well, there are a couple of ways to confirm that. Depending on the size range that we're talking about, it's reasonably straightforward to know. If the particles are above 200 nanometers, there is essentially no Brownian broadening. But if the particles are below that size, if they're below 200 nanometers or so, then you can determine how much is Brownian broadening by running the same sample at 2 speeds. In other words, if you measure the same sample at 10,000 RPM and then at 20,000 RPM, the measurement time at 10,000 RPM will be 4 times as long. And that means that you'll have 4 times as much time for Brownian diffusion. So if you compare the distribution for those 2 measurements, one at high speed and one at low, you can judge how much the diffusion is contributing to the broadening of the band. And in fact, if you do the same thing at 3 or 4 different speeds and then plot up the reported width versus speed, you can project to infinite speed and determine how wide the sample actually is.
Okay, great, thank you. I hope this answers your questions, Nick. Marcus Wager he says, does temperature plays a role?
It plays a role in that we want it to be constant because temperature changes the viscosity of the gradient fluid. So so long as you're operating at constant conditions, constant speed, nothing is happening, the temperature of the fluid will be constant. But if the speed is changing, or if you just are starting the instrument the first 30 minutes or so, the temperature in the fluid will be changing, and so the viscosity will be changing as well.
Okay. Well, great, thank you. If you have any questions, please send them to me and I will make sure they will be answered. Alessandro Ponti, he asks, are non-polar organic solvent gradients available?
I'm sorry, Wendy, I couldn't hear. Could you say again?
Yeah, he says, are non or / polar organic solvent gradients available?
Oh yes, there are an infinite number of solvent-based gradients that can be used. I'm sure that your local representative can make some suggestions based on the medium that you want to use, but they are routinely used. Many people use organic gradients and both polar and non-polar materials.
Okay, thank you. Gert Schulz has another question. He wants to know, how would you estimate to measure higher density inorganic particles between 0.2 and 10 would DCS a good alternative to laser diffraction, for example, metal or ceramic powders?
It will depend a little bit on the density of the material that you're measuring and the size range of interest. But in general, if the particles are large and dense, for example, 10 micron metal particles, you would want to do the measurement in a gradient of higher viscosity so that the particles don't sediment too quickly. But there's no reason why you can't measure in that size range if you use the correct combination of gradient viscosity and centrifuge speed. We routinely measure materials with density of 5 or 6 up to multiple micron size with no problem.
Okay, I hope this answers your questions, Mr. Schultz. Benjamin Forster has a question about the low density measurements. Why is it necessary to use a heavy water when measuring a particle with densities greater than 1, when the ingredients ranges from 1.3 to 1.7 for approximately?
Well, I'd need to know the details. I'm not sure I completely understand, but in general, it is possible to use regular water if you can generate a suitable gradient. That is, if you can generate a gradient that is higher in density than the particles you want to measure, there's no need to use deuterium oxide. Deuterium oxide is advantageous because it increases the difference in density between the floating particles and the liquid medium. It speeds the analysis time and produces generally slightly better resolution overall because the analysis time is shorter. Deuterium oxide, I don't know about Europe, but here in the States it's about $1 a gram, so it's not very cheap, but you're only using 20 milliliters or so to do a campaign of multiple measurements, so it's not a large investment. I use it routinely when I have a sample that calls for a high density liquid. It's not terribly expensive, so I use it, but
Okay.
it's not absolutely necessary.
Okay, great, thank you. Mr. Vaughan asks, if my CPS distribution goes negative size, for example, below 0 size, is there a problem with the test? Does it indicate a problem with the test run?
It indicates a problem with baseline stability. And to help resolve that problem, we need to see some exported data files. Usually when we see an exported data file, we can tell pretty quickly what the problem is. In general, the issue is that the baseline is drifting, and it's not drifting in a time linear fashion. It's drifting in a non-linear fashion. It's basically generating a curved baseline. And when the software tries to deal with a curved baseline, it either goes up or goes down artificially. If the baseline drift is linear in time, it's absolutely no problem. But if the baseline drift is non-linear in time, then we have to identify why that is happening.
Okay, thank you. Mr. Picot asks if the gradients. Oh, just a minute, please. Mr. Picot, the gradient is kept by rotation, so the instrument has to be operated without interruption? Question mark.
Yes. You can of course stop between campaigns. You don't have to run forever, but if you want to run a series of samples, of course you would not stop between the samples. It would run continuously through the samples. If the question is about infinite lifetime gradients, the answer is yes. If you want to have an infinite lifetime gradient, the disk must be spinning continuously during the whole of the time, because that the g-force generated by the disk is balancing diffusion of the material. So in the case of an infinite lifetime gradient, you have to run continuously for as long as you want.
Okay, thank you. Well, if you need more explanation about that answer, you can always send me more questions, of course. I have another question from Nedolkovsky. What difference does it make if there's a broad distribution of various irregular particle shapes?
Well, you've got a couple of things going on. When the particles are irregular in shape, it means that they are going to have irregular scattering properties, which is one issue. But the other issue is that a particle of the same volume will not necessarily sediment at the same speed as another particle, just based on differences in shape. One of the things that, one of the tricks that you can use to identify if you have problems with this is to measure the same sample with irregular particle shape, measure at a couple of different speeds. If the reported distribution changes significantly with speed, then that presents a problem. But if you find that changing the speed doesn't change the reported distribution very much, then you can be confident you have at least a reliable fingerprint of what the distribution looks like. Just a quick comment about this. Irregularly shaped particles cannot be characterized as with a single number. You can't say that there is a a number that is an accurate representation of a particle that's not spherical. So when we say the size and we report it as a diameter, please understand that we're talking about a simplification. Irregular particles don't have one parameter. They have to be described by multiple parameters, and there are no instruments, maybe except electron microscopy, that is going to provide that information to you.
Okay, well, I hope this answers your questions, Mr. Nedokovsky. We have a question from Mr. Diaz as well. What is the typical reproducibility when doing several replicates of the same samples? So how can I warranty if it is error of the instrument and not the particles agglomerating while measuring? What's the sensitivity? Well, it's going on and on. What's
Yes.
the sensitivity of the technique? Can I differentiate thin coating of 100 nanometers on a core particle?
Okay, I would need an hour probably to answer that series of questions. Could you start with the first one again?
Yeah. What's the typical reproducibility when doing several replicates of the same samples?
Okay, if you have a validated procedure and you're reasonably careful in execution, typically the mean size will be reported within plus or minus 2% over a series of runs, and often much better than that. For narrow peaks, the peak location will always be reported better than plus or minus 2%. A typical reproducibility would be approximately everything within plus or minus 0.5%. That's typical. Now, there may be extreme cases where there's more variability, but generally the measurement does not have much influence. And with regard to aggregation, aggregation during the measurement is extremely rare. And the reason it's rare is because the particles spread out very fast during the measurement. And so there's less probability of aggregation. Any aggregation that's taking place would be more likely to take place in the sample prior to measurement than in the measurement itself. I have never seen a single instance where there was aggregation during measurement.
Okay, and then his last question, what's the sensitivity of the technique? Can I differentiate thin coating of 100 nanometers on a core particle?
Depends on the size of the core particle, but yeah, we routinely measure the coating thickness of, say, polymer beads that have protein on their surface, or gold particles that have protein on their surface. It's a routine test. Lots of customers do that. It's certainly possible to do, and once again, it depends on the size. If you're talking about sizes in the sub-micron range, 100 nanometer coating is huge. You'd see a gigantic change in reported size.
Okay, well, Mr. Diaz says many thanks and great presentation.
Thank you.
I have one other question of Simone Pluis. I think she or he, I don't know, asks, what's the value of R?
The value of R, the radius of rotation for the detector is adjustable. On a typical setup of the instrument, it would be at approximately 43 millimeters from the center of rotation. That's a typical setup, but it's movable. You can adjust it. It doesn't have to be at that location. Typical setup is about 43 millimeters from the center of rotation.
Okay, thank you. One other question of Simone says, thank you as well. Mr. Bartosevic, he asks, does the refractive index affect the size measurements?
It doesn't affect the measurement of the sedimentation velocity at all. The refractive index changes the reported weight. So if you had a distribution over a range of sizes with an incorrect refractive index, the relative weights of different portions of the distribution would be incorrect. And so we say that the size measurement comes from sedimentation velocity, but the weight quantity comes from light scattering. And so to get the most accurate results, you have to have those two both correct. For very narrow peaks, for example, polymer beads that have narrow distribution, you don't have, the reported size will be very accurate independent of the refractive index because the peak is well defined. But with broad distributions, you'll see changes in the reported distribution based on changing refractive index.
Well, thank you. I don't think there are any more questions.
Okay.
I'll just wait 1 minute. Benjamin Forster wants to say thank you from his side for this great presentation. So I think everybody, thought you did very well. Thank you, Steve. Also, from CPS Europe and all the distributors, thank you for your time. I want to just remember that everyone will get a recording and a copy of the presentation. And if you have any questions, you can go to your dealer or just send them to me, and then I will make sure that they will get to your local dealer. I just have one question, a last question of Nedolkowski. Are large particles, e.g. 50 to 80 practically measurable, and if yes, how is it achieved?
Okay, 50 microns, I assume, is the number that's being discussed here. Generally, 50 microns is about the upper limit. It is possible to do, but you have to use a density gradient that has sufficiently high viscosity that the particles don't sediment too quickly. At this size range, the problem becomes what is called stochastic noise, and the issue is that when you inject a sample, there are not enough particles in the sample because the particles are very big. There are not enough particles in the sample to form a truly continuous distribution. And so you begin to see holes, you begin to see noise in the distribution as the individual particles go by. That's called stochastic noise. And the only way you can solve it if you want to measure really big particles is you have to measure multiple times and then average the multiple measurements to get a smooth continuous distribution. It's just you don't have enough particles present to get a continuous distribution when the particles are very big.
Okay, great, thank you. Well, that really was the last question.
Okay.
I want to thank everyone for attending, and thank you again, Steve, for the great presentation, everyone says. So I will be ending this webinar at this moment. If you have any questions, just send them to me. Thank you, and have a nice evening.
Thank you, Wendy. Bye-bye.
Okay, bye-bye.